Hello, everybody. Good afternoon, or good morning, or good evening, depending on where you are tuning in from. My name is Tina Myers. I'm a partner solutions architect here at AWS, and joining me today, David Daniels.
Hi, thank you, Tina. How you doing today?
Pretty good. How are you doing?
I am doing awesome. I just moved, so that explains the bare walls and the blank shelf. So getting settled into my new home. So yeah, good stuff.
Very nice.
I could tell you
We
all about that, but interesting. I think you have something more interesting to talk about, don't you?
I think so. I think we might have a partner hanging out in the wings. David, what's Howdy Partner?
Howdy Partner. Oh, I'm so glad you asked. So, Howdy Partner is our weekly show that we do on Twitch and now LinkedIn. And we bring partners on and we discuss their solutions and we show everybody all of the cool things that they're doing and some of the awesome benefits that they get from partnering with AWS. So,
Very nice. All right, let's go ahead and I think we'll welcome our next guest. We have Perminder Singh, who is a senior partner solutions architect for Quantum. Perminder, how are you today?
Good. How about you guys?
Good.
great. I'm always happy to see you, Perminder.
Me too. You guys are become my extended family doing this show on Twitch with our quantum partners.
Yeah,
And
I,
thanks
I
for
know that. Oh, sorry. Yeah, I know that whenever I see you on a Howdy Partner show, that I'm about to have my face melted with all this amazing quantum.
sure. And our partner today is Quanscient. They are from Finland, as you know, one of the happiest country in all the world. Lovely team. We started this relationship with them year or so, and we worked with them to launch a solution called as Allsolve. And those who are familiar with the methodology or mechanism we have in place for our partner is AWS Partner Network. And this solution Allsolve is a first grade solution in terms of we ratified and we validated the solution and did a foundational technical review. So it is available on AWS. It is built on AWS Cloud. Now, Allsolve is for those folks or those companies, researchers who want to do some of the simulation, complex simulation. If they want to get it down from days to the, kind of like a hour, and if someone don't want to pay for upfront license fee and they want to go pay as you go model, as well as if you want to run many simulation in parallel, you want to try every combination of your design, so this solution is for them. So without further ado, I think let us invite Consent team on the stage. Welcome, Juha and Asser.
Awesome. Welcome, guys.
Thank you.
Thank you.
Thank you. Happy to be here. And thanks
Really
for
nice to
the
be
great
here.
introduction, Perminder. And
Thank
good
you,
night
thanks for
from
doing
Finland.
this. I know it's midnight there, so but and then we are privileged to hear from you, on this solution. And all, we're happy that our audience love the fact that we have partners from all over the world now. So please continue.
Yep. So just a short intro, I guess, on our side. So I'm Juha Riippi. I'm the CEO and co-founder of Quanscient, and my background is more on like classical software engineering, but luckily there are way smarter people than me in the company working on the quantum stuff. So we've been able to do some impressive stuff there, but also in cloud computing. But let's talk more about that later.
Yeah, and so I'm Asser, Chief Software Architect and one of the co-founders in Quanscient. So not the quantum guy either. We have done some studying with our chief scientist about quantum computing, but we are still pretty far away from his skill level. But I'm pretty good on the cloud architecture side.
Great.
I'm curious, all the viewers, if you want to put in the chat where you're from. Wonder if there's anyone else from Finland watching it.
Sure.
We get some worldwide viewers and some nationwide. It's pretty cool. So let
We
us know
do.
where you're watching from, and any questions you have. We like to have it interactive.
Yeah, definitely. Any questions that you have during the show, please make sure you drop them in the chat and we'll get them answered while we're going. All right. So, Juha, I know you had said that you had some things to talk to us about how Quanscient got started. So I will go ahead and pass the floor to you.
All right. Thanks, Tina. So, yeah, Quanscient, we got started a bit over 2 years ago. And yeah, based in Finland, as we established, actually in a city called Tampere, which is about 2 hours north of Helsinki, the capital. And basically, the founding idea of Quanscient was that let's do something cool with quantum computing. But for some reason, that wasn't quite enough to get like pre-seed funding. So we had to come up with something a little bit more specific. And I think the first founders I met with Quanscient, they were Asser and then Valtteri, who is now our chief scientist. And Valtteri was a quantum researcher at Aalto University at the time. And Valtteri was working in IQC Labs, and that was a research group that was headed by Professor Mikko Möttönen. And Mikko went away and was one of the co-founders of IQM, which is kind of the European leading quantum hardware manufacturer. So that kind of got Valtteri thinking that he could actually try his wings in the startup world as well. And then we met. First, this was me, Asser, and Valtteri. Kind of started playing around with ideas on what we could do. And one of the big ones was kind of multiphysics simulations with quantum computing. That wasn't the topic that a lot of quantum companies were researching too much. Some were doing something in the area, but Valtteri had also written a paper about that, or I think it could have been a couple of papers in his academic days. And also Asser and Valtteri both had a strong background in classical multiphysics simulations. And when we're kind of in the quantum world, by classical, we always mean the regular computing, cloud computing, not quantum. So if I say classical, that's it. So, but then we met our current CTO and co-founder, Alexander Halbach. And Alexander had done his PhD on the topic of how to distribute multiphysics simulations in the cloud. So that got us thinking that we could actually kind of start the company on two pillars. So start building a B2B SaaS product that offers multiphysics simulations with very high efficient cloud scaling algorithms. And on the other pillar, start researching the quantum algorithms on how these could, in the near future, be implemented to provide real business value and kind of the exponential speed ups that quantum can provide, with the vision that will combine them into a hybrid product that has both cloud and quantum computing in them. So that's kind of the founding story. And yeah, that's what we've been at it since.
Great. How many team members we have in your team? Like total employees? At the moment.
Totally. At the moment, we have 23 employees.
All of them in Finland, or there is other office?
No, we're actually quite an international bunch. So I think we have 9 different nationalities. Most of the people live in Finland, but then we have a couple of people in Germany, one in Switzerland, and one in Serbia.
Oh, wow. All over.
All over, and maybe soon in the United States as well.
Sure.
Very nice.
Yeah, I saw someone asked in the chat, how do you pronounce my last name? It's Lähdemäki. Might be a bit difficult if you know.
Lähdemäki. Okay.
Yeah.
Sure.
translates to spring hill, I think. Like,
Yeah, exactly.
Nice.
All right. Anything else you wanted to add in there before you get started talking about your Allsolve?
well, I think that pretty much kind of covers the founding story on how we got about that, and maybe just a little bit on, because we're a startup, so on the phase. So far we raised about 6 million, and now gearing up towards our Series A with the goal of raising that in the first half of 24. So
Yeah,
Nice.
best of luck.
that's kind of stuff.
Good luck with that. That's
Yeah.
exciting.
Thank you.
Yeah, it's been a great ride for 2 years.
Absolutely.
All right. Well, then let's go ahead and start talking a little bit about the Allsolve solution that I think you guys are going to be showing us a demo of a little bit later today. So what is that all about?
Well, I could show you, I promise, 2 slides. That's it. No
Okay.
more. I mean, it's the CEO syndrome. I love to show slides, but let's just keep it at 2. But just to give you an idea, and before going into that, maybe just because there might be somebody listening who kind of doesn't immediately know what multiphysics simulations is all about. So it's basically a very vital engineering tool, and how they are typically used is, well, let's say that you're a designer working on a new electric motor design. You typically draw or design your product in a CAD tool, so you make a 3D model of it. And with multiphysics simulations, you can take that model into the simulation software and actually simulate how it works in real life. So basically build a digital prototype out of that, which then again, of course, it's a very kind of, it helps a lot in the engineering cycles. You need to build less physical prototypes because you can kind of evaluate your design way further with just simulations. And why it's called multiphysics, not physics simulations. It's basically because what areas are typically covered are 3. There's electromagnetics, there's fluid dynamics, kind of on how fluids or air or anything like that streams, and then there's the mechanics simulations. And if you go back to the electric motor, if you want to build a digital prototype, a simulation of that, you need to simulate how it works electromagnetically, kind of what kind of torque it produces, all that stuff, the voltages and, well, whatnot, and how it works thermally. And thermally is actually kind of a fluid dynamics problem because there's typically cooling in the motor. And that has an impact on the electromagnetics and vice versa. And that's the third part, how it works mechanically. So the structural integrity, where do you want to strengthen the structure? Where can you kind of save in material costs? So 3 different areas of physics, multiphysics. That's kind of where the term comes from.
Okay, that's interesting. So I could imagine all sorts of different types of use cases for this, but I'm going to go ahead and let you get to your show and save some of my questions.
So yeah, just a little bit about Allsolve and why we started building this. It's kind of, we see that even though this, as mentioned, the simulations, they're already used in very wide spectrum of engineering, like automotive, aerospace, semiconductors, energy sector, pretty much everywhere. But the thing is that the present day tools are starting to be a bottleneck in engineering. And there's some figures from a study made by one of the companies working in the same field as us, ANSYS, and they're saying that 78% of engineers need to constantly reduce the complexity of their simulations, which means that if we use, again, the electric motor example, they kind of have to strip the model of details, or they even might have to flatten it into a 2D model before they are able to simulate it, because there's just not enough computational capacity to do an accurate simulation of that. And that's a problem because, well, if you don't reduce the complexity, your simulations might not run at all, or they'll be running for days or even weeks. And then again, reducing the complexity, that's a manual task. It takes time, and then it reduces the accuracy of your results. And then again, 96% of engineering decision makers say that reducing time, risk, and cost is the most valuable thing in their R&D. And more accurate, more performant simulations is exactly the thing, because if you can get more accurate results, simulation results that you can rely on, you can make actual design decisions based on that data. Instead of sort of kind of getting some hints and cues, but still needing to build those prototypes, which take a long time. And then again, a big part of the engineering decision makers say that the current kind of licensing model, the traditional licensing model of this software, is also a problem. They need more flexible software licensing, so kind of things like B2B SaaS. And that's kind of the reason why we build Allsolve. And it's right now out there. We've demonstrated well over 100 times speedups in our simulations already, just with the cloud technology. Which means that the engineers no longer need to reduce the complexity, and their runtime just drops dramatically. We'll have cases like from simulation time dropping from 8 days to 1.5 hours, or from 3 weeks to 8 hours, while getting 3 times more accurate results. Meaning that the design iteration cycles of our customers are just dramatically faster, and they can actually rely on the simulation data. And of course, there are things like enabling automated workflows. So with cloud-based APIs and programmatic access, engineers don't necessarily need to, in the future anymore, rely on external simulation software. Instead, they could be directly integrated to, for example, the CAD software that they use to design, which automatically could trigger hundreds of simulations, kind of like DevOps and automatic testing in software. And of course, all that data that the simulation produces can be hooked up to machine learning algorithms to provide even kind of optimization tips for the engineers, or create surrogate models of the designs. So kind of building this kind of platform, and of course, enabling more experiments in less time. And then, well, last but not least, the quantum part, which sort of has the potential to provide these exponential speedups. So meaning, let's say I mentioned that aerospace industry is one place where the simulations are used a lot. So with the current present day traditional computing technology, it's practically impossible to compute the aerodynamics of an airplane accurately. So you need to build a prototype, you need to take it wind tunnel test it, and kind of iterate on that, and that process takes years. But with quantum, you could actually do it accurately with the exponential speedups, and that would be a kind of, well, I hate the revolutionary word; it's kind of overused, but that would be revolutionary for the for the aeronautics or industry. But yeah, that's the slide, and that's the reason why we build Allsolve.
Great. So is there any limitation when it comes down to like how big or small a physical material should be? Like I heard like you saying airplane or Boeing Airbus sort of. So it ranges from that to even the small motor. Is that true?
Well, it ranges from that to like semiconductor chips and individual transistor level simulations, actually. So the scale is just kind of from microscopic things to these huge airplanes.
Yeah, it's also like the size of the thing doesn't matter in that sense, but it's just the accuracy that you can get. There is this part of the simulation called meshing, where you have to divide the actual thing into these small pieces to be able to actually compute the problem. And for bigger things to get more accuracy, you have to use small elements for a huge thing, and that's what causes the impossibility to solve it in a reasonable time. Yeah.
I can imagine, right? Like I closely follow the Formula One. Always they talk about the air drag and all that. Like it's like a milliseconds or seconds difference between what Mercedes or Ferrari have and what others have, right?
And they are doing tons of simulations
tons of simulation.
Still, the accuracy is a problem there.
Yeah,
with classical computing.
great.
I was looking at your webpage here, and it says simulation runtime from days to coffee breaks. I love that. That's just super cool. But that is, I mean, that just allows people to innovate faster when instead of taking days running a simulation, you can do it in a coffee break, and you can do it multiple times a day. That just sounds amazing. So, yeah, I'm really impressed by that.
Yeah, exactly. It's like, I think we all can agree that humans work very well on this trial and error basis, much better than analyze for a month and then come up with a perfect solution.
Mhm.
We like to try things and see how it works. So instead of waiting for a week to see what your trial produced, you now have the coffee break. So
And then trying something over and over to see if it works isn't always. I mean, I think of crash testing cars, right? Like, how many cars are they going to have to crash into this wall? I mean, that's probably an expensive thing to do. So, like, if you had some sort of simulation, I'm not saying that there's probably a bunch of legal and stuff when it comes to car crash testing and all that. So I don't know. I'm not an expert on that, but yeah, I'm just thinking of many different ways that that could provide some sort of relief for companies that would be huge in saving costs and time and allowing faster innovation.
Absolutely, and actually, simulations are used quite extensively in crash testing cars. Kind of of course, they have to validate them still with real crash testing. That's probably regulatory reasons, and as a driver and a passenger, I'm still happy about that since they're not using quantum. but not really an area of simulations where we've gone, but kind of based on the same technologies that we're working on.
Great. And I saw something around NVIDIA modulus, and I'm assuming like this 100 times faster. So what is, without divulging your IP, if you can talk about what makes it 100 times faster?
Well, actually, that's not the part for the sample about NVIDIA was there are plenty of people doing that, but kind of combining physics simulation data with AI algorithms, and that's kind of a thing absolutely we're looking very closely into and starting to build things around that. But what makes it faster is kind of it's based a lot on our CTO's PhD, where he didn't invent domain decomposition method, but that's kind of the way we scale. So effectively, you could think about it like Asar mentioned the mesh. So we take the model, we mesh it, we make kind of a mathematical representation of that. And then with domain decomposition method, we are able to automatically distribute that into as many pieces as needed. And each of those individual pieces are solved on individual CPUs. And that scales next to linearly. Of course, it depends a little bit on the problem, but we've got very good results out of that. And the nice thing about it is that we don't really need like HPCs to run these things. We're using quite simple EC2 instances, kind of these 2 vCPU EC2 instances, but we just use a ton of it. And that also solves another problem with simulations, which is memory. That's kind of often the bottleneck, because, the mathematical method we use for the cloud simulations is called finite element method, and that's a very memory-hungry method. And once the simulation complexity grows and the simulation size grows, the memory consumption kind of grows exponentially. But we're able to use distributed memory with these EC2 instances, and that gives us a huge memory pool. If we use, for example, 1,000 CPUs with 16 gigabytes each, that's a whole lot of RAM available. And it actually also reduces the overall memory consumption of the simulation because we split it into pieces, and that kind of reduces the complexity of these individual simulations that are run on different CPUs.
Nice.
That's interesting that you're able to just run all of the stuff on EC2 instances. And it sounds like relatively small EC2 instances.
Yeah,
That's crazy.
exactly.
Mhm.
And the thing is that DDM, the domain decomposition method, it's kind of well known in the scientific community, but there is of course many ways to do it, and the way we are doing it is like it's not so much network intensive, which is why we don't need like the regular HPC, like what was it called, like elastic fabric adapter, which gives you like super good small latency and stuff like that.
Yeah.
But we can just use the regular network adapters, and it doesn't slow it down.
That's really cool.
Yeah, if you can do this with a normal EC2 without like a A100 GPU, yeah, there will be a lot of cost saving, right? Like a lot of cost saving. Good. I will read about domain decomposition. I haven't I haven't read about it. Interesting.
Oh yeah,
Yeah.
there should be plenty of publications about that.
Well, I'm excited to see how you pull it off. This is really interesting.
Right.
Just excited to see how it all works.
Yeah, so well, it's looking positive in the way that we have. I mean, we launched the product early this year, and we've now onboarded our first customers, and the feedback has been overwhelmingly positive. So that's kind of it really. I mean, they say that you kind of feel when you have product to market fit. I wouldn't go as far as saying that yes, we have reached product to market fit, but we're starting to feel it because the users like it, and there's seems to be a good kind of like engagement factor. So they're also using it a lot.
What do you look for in a customer of Quanscient? Like, what are there any limitations to that, or is it anyone at this point? How does that look? How do you select your customers?
So at this point, out of the kind of three main sectors, we are focusing on the semiconductor and the energy sector. So we're working with fusion energy companies, which is, in my opinion, it's really inspiring to work with, or at least have a small part in something like that, which could, well, give endless clean energy to the mankind. So where they use our product is kind of simulating their superconductors, which then contain the plasma. And then in the semiconductor side, it's been mostly the focus has been on MEMS, which is like micro electromechanic systems. So things like gyroscopes and microphones, RF filters. Basically, every cell phone has dozens of those devices. And it's a rapidly growing industry. And there are plenty of use cases for simulations there.
Nice.
Yeah.
Means we at Amazon also. Please continue.
Yeah, the applicability of this is like very wide range that we can go from these devices that are the size of your thumbnail, and then these fusion reactor prototypes that are like 20-meter radius or something.
Yeah. Now, since you say fusion nuclear energy, it is applicable to the wide variety. And on the energy side, at least on the AWS side, I think we try to focus how to make solutions which are more sustainable, right? We have signed up for climate pledge. We are working to replace our Amazon side the delivery of the packages with a full electric vehicle and all. So any partner or any customer who work in the similar area, so we're happy to see that kind of a initiative.
Yeah, and that's actually kind of a good segue on quantum and the sustainability side of that. So there's a lot of use cases for quantum, but what we're focused on is like one area of multiphysics right now, which is computational fluid dynamics. And I don't have the accurate percentage, but I can with confidence say that a majority of the world's supercomputing capacity is being used to run computational fluid dynamics things, like climate modeling, these, F1 cars, airplanes, all that stuff, because it's a very complex problem and it requires a huge volume of supercomputing capacity. And of course, that's not the energy that those machines need, is not free. And so quantum can have a huge impact on that. I mean, of course, quantum machines need energy too, but they're so much more efficient in computing these tasks that can have a vast impact, but of course also enable us to do these way more complex calculations. For example, with climate modeling, which I mean is a pretty important topic on the research and on the sustainability side.
Yeah, definitely.
Okay. So what do we have next, Tina?
So I think I know I would love to see a demo. I don't know
Before
how
going to the demo,
Yeah.
would you like to hear about our infrastructure? How did we
Oh, yes.
get where we are right
Definitely.
now?
Yep. Yes.
Yeah, I can give you a short history of the
Yeah,
cloud
please.
tech
Sure.
behind the
Are we
Allsolve.
sharing anything on the screen for this one?
Not for this one.
Okay,
So
that's fine.
yeah,
That's
so
good.
basically, yeah, in the January 2022, we started with a proof of concept, which was basically a small Python backend that reserved single EC2 instances, and then React UI coded by Juha, which was basically two buttons and a text field. and this is what we actually showed to our first customers. And
well, they say that kind of you should get the product out there when you're a little bit ashamed, but I was very ashamed.
yeah,
Nothing wrong with keeping it simple.
Yeah.
Yeah, you can soon see that we have come pretty far from those two buttons and the text field. Then the next thing was that it was a single instance, and of course our secret sauce is the DDM. So we started looking into how do we do the instance reservation and handle the multi-node jobs. And what we came across was AWS Batch, which was a really fast solution for us to build on. And that's where we went, and it served us very nicely for like 6 months. We built like some services around it, some job scheduling of our own because we had some special needs. But basically what that scheduler did at that point was just to queue jobs in batch and get the results from there. But the problem we started having was that when you are doing the simulations, you initially do like a bunch of small simulations just to test it out and see that you're getting something sensible before you go to the actually really accurate one with a huge number of unknowns. So the startup delay in batch, we couldn't reduce it below like 2 to 3 minutes. It was okay if you did a huge run because it would take like a long time anyways. But if you were doing these 10-second runs, then the startup delay started getting like a bit painful there. So we eventually moved to pure ECS. So what we did was we have ECS clusters where we have some warmed pool instances, and those like start up really fast. We are based on Docker containers, so we just preload our images there, and it works really nicely. But with that, there is the negative side of having the pool instances running constantly, and we don't have good data yet on like. Eventually, we hope to see such amount of usage that it actually makes sense to like keep this pool quite big, but at this stage, not yet. So what we also did was we created the Lambda system where you can actually run the simulations in Lambda too. And this works really nicely for the small jobs. It runs really fast and basically scales automatically.
Okay.
Yeah. And
from pure infrastructure to serverless journey. Good.
Yeah. We did hit some small blocks there on the way, but so far we have managed to cover all of them. We did receive some very nice help from the AWS architects too, through the partner program. It was really useful for us. And basically what we now have is the Lambdas and then the ECS with the multi-cluster setup, because there was this limitation of 5,000 vCPUs per ECS cluster, which kind of becomes a limit for us pretty quickly. And another thing that we had to overcome was that there are some rate limiting in the AWS APIs naturally.
Yeah.
But and they are a bit strict by default, but contacting the support and the AWS architects, we managed to raise them, and I think we still need to raise them again, but it looks like it's viable that way, which is pretty nice.
Great.
So you've gone through the whole combination of technologies, starting with regular servers and then going into containers and going into serverless. You've experienced it all.
Yeah. We've been throwing out the stuff that we did last month, basically.
That's what I was going to say. You've gone through all of this in a short amount of time too.
Yeah.
So you've just been constantly going and busy and moving. So
Yeah.
You start one thing and it's on to the next, right?
Yeah. After 2 years, we are finally reaching some stability. We are good to go with this current infrastructure for, I don't know, at least a year. But the next thing for us probably is something like Kubernetes. But we didn't go there straight because we don't have any Kubernetes expertise yet. So in that sense, the basing our stuff on the AWS ready services has been really good for us.
Very good.
By the way, there was a comment there about the name of the algorithm used. So that was domain decomposition method, if meaning the one how we distribute the computation.
Yeah, there was also a comment that don't go to Kubernetes problem. So that's a kind of what we felt like and didn't go there. Because it's notoriously hard to config and
yeah.
So now, how long have you been part of the AWS Partner Network? When did that begin?
Quite early, I
Quite
think.
long. I think we
Yeah,
started in the August 22 or something
22.
like that.
Yeah.
Yeah,
Okay.
that's probably right. Yeah.
Nice.
Yeah, I think you guys were talking with my business development Saf and Zhang before even I joined the quantum team. I just moved in September and then I was just warming up the transition and all. But by that time I was there, so he was warming up like, hey, here are the tracks we are running with. And then I think he mentioned Quanscient. I'm sure like it was August of 2022 before my joining this team. Good.
Very nice. So how has the partner network journey been for you so far? So you joined back in August, and I know we saw the request for Howdy Partner a few months later. We were booked out for a while there.
Yeah.
And I think that the timing is great now. It's I think a few months ago it could have probably been a little early. Say, I think we're way further now, but well, that's of course always true with startups. I mean, things move fast, but yeah, the journey's been really good. So it's I mean, I was very positively surprised about the sort of attention that AWS pays also for startups. Building kind of on the early phases of building. I mean, I think we were pre-product. Well, yeah, we easily were in August when we joined. So it's any request we ever had, it's basically the responses are practically immediate, at least if you consider time difference between US and Finland. And now we also have like a dedicated account manager. We have regular meetings with the team, including the partner team. And we've also utilized the ACE program, like the co-selling program, and actually got in touch to some of the AWS account managers who are responsible for some of the clients that we would like to be talking to, and kind of discussing there on what would be the best strategy for them. And so, and of course, all the technical advice. I think Asser is probably a better person to discuss about that side of things. I'm more on the business side, but
Well,
absolutely.
as I said, we really had great support from AWS architects. We went to AWS Summit in Stockholm last year, and this year we met there with our latest AWS architect we've been in touch with, and had a 1 hour chat about our architecture and got like confirmation for our solutions and also our future ideas, and it was really useful.
Excellent. That sounds great. So one interesting question in the chat: when you hire today, what skills are you looking for?
Well, there's a wide range of skills, but of course, basically, we have 3 technical teams in the company. There's the cloud development team, which is Asser's team. So that's mostly like cloud development skills, of course, AWS knowledge, DevOps skills, front-end, back-end. We use, well, you can talk more about tech stack, so I don't make a fool of myself. But
yeah, I would say currently the cloud team is 6 people, including me, 1 designer, and then 1 junior developer and 3 senior full stack developers. So at this stage, we still don't have like any specific roles, but everybody is kind of doing everything. Of course, we have like there has been forming this ownership of different areas of the whole system, but we are looking for full stack experience. But if we were to hire, currently we are not hiring, but when we hire next, I think what we want is someone who is inclined to DevOps and security side of things. We are pretty good on both, but it's taking a lot of time, and I think it would make sense in when possible to have dedicated roles for both of those.
Mhm.
Yeah, and I guess in terms of languages, so the backend we have that's written mostly in Go, and then the front end is Vue.js.
Yeah.
View.
Yeah,
So
the tech stack is basically, yes, all of the backend is in Go now, and front end is Vue.js, as you said, and then we have a few extra pieces that are worth mentioning. We use VTK.js, which is a visualization library, and that plays a big role in our UI, visualizing the geometries and simulation results. And anything else worth mentioning? No, maybe not. Yeah.
Yeah, and then of course there's the other two technical teams. So there's the quantum team for sure. So that's quantum computing, mostly like physics background, mathematics background, and then the kind of the classical side, physics algorithms, and also this like sales engineer or professional services team. So they help our customers in their physics simulation problems, but also, of course, develop the algorithms and create benchmarks, demos, examples. So they also typically have a physics background, like a lot of PhDs in those two teams. And well, of course, there's also the business side of things. So we are just onboarding our first like dedicated salesperson, VP of sales, and he has a background in physics as well, and has been kind of experienced in selling similar products. So a really good match for us. We're excited too.
Just a clarification on there was the question, what languages you use for heavy processes. If by heavy you mean the actual simulations, the library solver we use is based on C++. Also, the meshing library is C++. So there is like this old language side to this.
Great.
And I'm not familiar with either Penny Lane or Circuit. Sorry.
Yeah.
I want to go back to for a moment. Go back to your partner journey. I just had a question about that. Let's imagine, if you will, that the AWS genie is tuning in right now. Is there anything that you would wish for, that any kind of features, anything in the process? Like, what would you wish for, and what do you think we could do, that could help you in your specific situation?
Some more credits would help.
What's that?
Some more credits would help.
Talk with our business guy. I named him earlier, but yeah.
I think the AWS genie just left the chat. So.
Oh, too bad. Maybe Acer has some more like on the feature side of things. I guess the throttling has been sort of a challenge for us.
Yeah. I think the process of getting the API limits increased is it's slightly on the slow side. I kind of understand that it's difficult also on the AWS side, but especially for our use case where the workloads are, so to say, bursty, the rate limits can become a delaying factor in launching the jobs.
Yeah.
And
Great.
well, of course, one thing is we are really kind of course, keeping a keen eye on AWS Bracket, the quantum side of things, and adding more access to more hardware, getting more like hardware manufacturers there. And we've been using it already to run some of our quantum algorithms. But that's always, of course, a plus, because on the quantum side, the strategy is to work with a lot of hardware manufacturers and kind of experiment on different platforms, because they do give different kind of results, and with some we have been very successful, and with some a little bit less so. It depends really on the cubic topologies and stuff like that.
Sure. Yeah, and I think just to answer that penny lane question. So penny lane is this whole software package from the Xanadu, the photonic based provider who we had earlier in the bracket. Now they are, they're fixing the next version of their machine. But
Right.
penny lane is heavily used in the quantum machine learning topic, like regression or classifications tasks. Of course, Circ is Google's, right? So we are AWS, so Circ is not out of question there. Yeah, so we have variety of hardware, right? From IonQs, Rigetti, and even the neutral atom, the Rydberg atom-based machine from Cura. But yeah, it looks like I think this would be a good segue to now see the demo.
Yeah.
And our audience is probably itching for the demo.
Sure.
I know I'm
just
excited
to
for it.
mention, I think we have written most of our quantum algorithms in Qiskit.
Yeah. So Qiskit as a programming language, we have adapter, bracket adapter, our own. We manage that adapter, but then we support Qiskit adapter for the open source version of that, because we believe in open source too. So if you're a Qiskit developer, you can use the Qiskit adapter to submit the task, but that is not managed fully by AWS. It's open source community. But if you're a bracket adapter, it is managed by us. There will be a quick runaround on fixing the bugs and things like that.
Right. Yeah.
Great.
So if you, Tina, can
Let's
put my
add your
screen
screen to the
share on.
stage.
So here's the main view to our product, Allsolve. And
So I see a screen. Okay, now it comes. There is some delay, I guess. Network is delaying on my side.
Yeah.
I see now.
Yeah. So there's the basic project view. I have a couple of example projects here. We have these ready-made demo projects of different kinds of physics setups, like for electric motor, then some superconducting wires and their studies about their properties. And I just copied a couple of them here just to show you some examples before actually doing something live. So this is the electromagnetic wave cavity resonance, and we have done an eigenmode analysis, which means that there is some certain modes that a electromagnetic wave can resonate in some geometry, and what this simulation finds out is the modes in which the waves can resonate there, and you can visualize, you can see the modes. It might not make much sense to you if you don't know much about electromagnetic waves.
Yeah, but basically, like resonance modes and eigenmodes, it's an important thing to discover in the design phase, because if you kind of have for example, your materials have the similar resonance frequencies that can start causing problems. It's kind of similar as in that there's an example about bridges collapsing when like wind is blowing with a certain speed, and then it's hits the resonance frequency and it sort of just accelerates and the structure collapses. So we're still it's basically the same effect.
Sure.
Yeah.
Basically,
in this case, it's a desired resonance. So
desired
in electromagnetic waves, it's often desired because that's basically how we do any kind of radio communication.
Okay.
Yeah. Maybe
And
we
then
can
we
look at
are basically checking the tensile strength of the material, right? Like how much frequency it can, which can take and all. Is it like that? Okay.
Yes, that's possible. We have, for example, this eigenmodes of fan blades. Can make a quick run on that.
Maybe you can actually, while it's running, also show kind of how it's set up when you kind of where you can import your step files and kind of where the geometry is defined, and then sort of on what kind of physics you can add to the problem.
Yeah, I was thinking about actually making something simple. So let's make a drum head simulation. So you could start with a geometry file, but I'll just make a simple cylinder, which will be our drum head. Let's say it's 20 centimeters radius and 2 millimeters thick. Don't know if that makes a good drum head, but let's see. And for the material, we can just pick one of these ready-made ones. Let's say it's made of aluminium.
Nice. I was about to ask this question. Where do you pick the titanium versus the fiber carbon, all that? Okay.
Yeah. And you can, of course, also fine-tune a lot about the material properties. So you can pretty much do anything, like all the physical properties that are relevant.
Okay.
Then you can also make it anisotropic, which means that it can be different in different directions and very complex things like this. But yeah, basically we have like this tab model here that you have your geometry model. You can do some simple operations here, add basic shapes, do some translation removal, copying of the objects, and then some Boolean operations on them. And then you have the properties where you can define shared expressions, which are basically, they can be functions that take arguments, and you can use them in the various places in your problem definition. Or they can be just constants or variables that you want to sweep over. I won't be using.
Yeah, and sweeping is kind of, let's say that, well, if you're, for example, designing, well, we work a lot with MEMS, but let's say a transducer that operates with different frequencies, you can kind of make a shared expression of the frequency, and by sweeping we mean you can evaluate how it works in different frequencies, and of course all those simulations would be running at the same time. So that's kind of additional speed up to, as we can accelerate one simulation with domain decomposition method, but then we can run as many of them at the same time as is needed.
Yeah. Great. So then the setting up the physics, we have a quite nice set of physics already in the graphical user interface, but since we want to know the vibration modes of this drum head, we'll pick solid mechanics. and we'll add these are called interactions. So these set like, for example, some force to it or constrain it from some point. And in this case, we want to clamp it on the surface on the side to simulate it being attached to the body of the drum. And that's all we need for this. And then we do the actual simulation. This was which we already discussed shortly, the meshing part. Let's do that first. So this is a step that is just needed to make the actual computation. It breaks the geometry in this kind of smaller pieces.
Okay.
For example, this is very small problem, but it has 28,000 pieces.
Okay.
And then we'll do an eigenmode analysis. The last 5 and the eigenvalue magnitude can be 0. And what is sort of special in Allsolve is that we are sort of script based, and everything that you define in the graphical user interface is actually translated into this simulation script. And you automatically get like all of your regions that you defined in the UI here, and you can use them in the script. And if you enable the scripting mode, you can add your own simulation formulations, completely customize it, or do whatever.
And that's all Python, so it's kind of
yeah. So as I said, the actual solver library is written in C++, but we have this Python wrapper for it, which is utilized here because C++ is a bit hardcore for many people these days. So
yeah.
Then we define some outputs, the eigenvalues and the displacement field. Then we can run it. This is the log from the simulation solver.
Okay, so at this time, like whatever it was breaking into that 1,000 pieces, so it's being sent now, and the results are collected back.
Well,
like
actually, in this case, it's so small that we don't have to break it into pieces.
Okay.
If it were a bigger one, you could actually here say that you want to calculate it in 1,000 nodes. Basically, we are in the works of making this selection automated. It's not an easy problem to take the geometry and the problem definition and make this optimal. But basically what is sort of optimal is about 200,000 sorry, 200,000 unknowns per node. In this simulation, we only had about 100,000, so one node was fine.
Okay.
But if you would have like, I don't know, 5 million unknowns, then you would use 25 nodes or so.
So now we actually, in the result, so we know if you have a aluminum drum head, what was it, 1 millimeter or 2 millimeter thick, and you whack it, it resonates with, what were the frequencies again?
You can see the frequencies here. So
those are the
first
harmonics
resonance mode is 125 hertz.
Okay.
and then you can see what would the resonance actually look like, how would the drum head actually vibrate.
Okay. And then the color here, as you're seeing in the vertical bar, so it's like the blue is better, and then whatever is going red or amber, it's like
That's
it's
the
Blue
material
here,
under
mechanical.
stress.
Yeah.
yeah,
Okay.
the 0 means that it stays put, and
Okay.
then the red is that it's moving. So it's the magnitude of the movement.
I think you can enable the warping filter, which kind of exaggerates the movement. So then it's you can actually, well, there you go. It's
Yeah.
now it's of course
This is
super
very
exaggerated.
but you can see how it actually moves.
And this eigenvalue, whatever we were saying in the context here setting, it is the energy state, right? And what we are trying to do is like get the lowest stable energy state for that particular material, because material is very stable at a lowest energy state. Is that the concept here?
I would say it's not about the energy states in this case. The eigenvalues in this kind of simulation, they pretty much are the same as the resonance frequencies, which are also called eigenfrequencies. So the why is it called eigenvalues is just it happens to be so that the eigenvalue formulation gives you these resonance frequencies. So
Okay, gotcha.
yeah.
But we want this as blue as possible, right? Or is it?
Well, in this case, we
no.
just want to see, like, for example, now because it's attached to the drum body from the sides, we don't want that to move, but we
Yes.
want to see how does the
Okay, vibration.
drum head
So-
vibrate up and down.
So basically, let's say you're designing some mechanical system where, and so you you kind of want to know what the eigenfrequencies are, because there could be, for example, it could be installed in a place where there's, for example, background noise, and you don't want that noise to be identical to the eigenfrequency, because that will cause these harmonic vibrations, and it will probably, if it's a sensitive device, it will mess up. It might even break it, or at least it will cause it to malfunction. And then with kind of iterating here, you could, for example, try various designs where it would be, for example, clamped in a different way, or the geometry would be a little bit different, so you could manipulate so that the eigenfrequencies are something that don't appear in the environment where the device would be normally used.
Yeah.
Okay.
So that's
and after finding out these frequencies, you could pick one of these frequencies and then do a so-called harmonic analysis. So you could actually, for that, you would put this thing into air so that you could actually see that when it vibrates, what kind of sound wave, acoustic wave it is, like sending out. And you can also do that in this software. You have the acoustic wave physics, and then you can add this acoustic structure interaction, which will connect it to the solid mechanics.
Yeah.
Okay.
But I think for that we just need to draw an airbox around it, so the waves would have some material where they actually move. And that's actually a big reason why there needs to be this kind of manual thing to add, because if you import, let's say, your CAD design in there, and then you want to simulate, let's say, something acoustic, you want to add a box that is filled with air around that object, so there's a physical medium for the air to travel.
Yeah, here is an example of that. So in this case, we have taken this coil as this geometry file called step format, and then we put this box around it, which we then make air, and then we have make the coil aluminium and have a steel core inside the coil.
Okay.
And in this case, we have made a simulation where we put a electrical current through the coil, and also simulate how it creates a magnetic field and then induces a current in this steel core. And the result looks something like this. So you can actually see how the magnetic field lines would go. They are shown with these
That's
arrows.
interesting.
Yeah.
And then if anybody's just joining, we are talking today with Arthur and Juha from Quanscient, and they are going over their Allsolve solution. And right now they're going through a demo showing us how we can speed up and improve the calculations in your multiphysics simulations. That looks really cool.
Yeah.
Yeah.
And when it comes to the big things that we can solve, I don't unfortunately have it ready here, but I do have an image from a presentation that we did we published a scientific paper in this one physics conference, and what you see here is actually what is called a stellarator, and that is used in it's a certain type of fusion reactor prototype, and this was 320 million unknowns, and it was distributed to 500 machines, and I don't think you could even solve it on fewer machines with that many unknowns, but it only took 15 minutes to solve for those.
Yeah, that's
pretty
really an example of
speed.
It's really an example of an kind of what used to be an impossible problem before Allsolve. So you definitely could not do that. So typically the biggest simulations you can run in traditional software are maybe 5, 10, 20 million unknowns. That's 320, and it runs in 15 minutes. So
yeah, and this is very complex problem and big problem, because all of these weirdly shaped coils are superconducting wires, which are highly nonlinear, and then you want to see how does the magnetic field behave inside this coil configuration, which is this magnetic field then contains the hot plasma inside.
Okay. Looks like a state-of-art thing. There are things or two I learned today, like, we are getting a crash course in physics.
Yeah, this is actually pretty well-known configuration, but it's still really hard to build so that it's stable. And there are
the thing with
strong forces on these coils, mechanical force caused by the strong magnetic fields, and many kinds of details where you have to take into account many areas of physics.
Yeah, if you think there's like tens of amps of power flowing through those superconductors, they cause very powerful magnetic fields, which again then start causing like forces to the coil. So kind of the structure is pretty hard to design. You need a lot of simulations for that.
Sure.
Yeah.
So this particular instance, once this all is done, right? Like looks like a lot of parameters, a lot of simulations and all. What do you guys did next? Like it was for a specific customer segment. Like I heard like nuclear, plasma and all that. It's like energy sector. who were the end customer who would use this and do the
Yeah,
real
it's-
build of the system?
Well, absolutely. Like fusion energy companies is a big segment for us, and it's also something that that requires these massive simulations, and there's really no other tool out there that can provide them. But then the other ones come more from the semiconductor sector, so kind of from these few big fusion reactors to very small things like microelectromechanical systems, in other words, MEMS, so accelerometers, microphones, different kinds of sensors, transducers, RF filters. Yeah, just for new people joining, like all of you have dozens of them on your cell phone, so it's a very rapidly growing industry.
Yeah.
Nice.
I guess unless there is more questions about Allsolve, maybe we could move to the quantum demo if Juha wants to present that.
I have one question for you before we move on. So I know you've mentioned throughout a couple of these different simulations there being a certain number of unknowns. So how do you or your customers figure out how many unknowns there are? And then do the customers calculate how many CPUs they would need, or do you guys do it for them? Like, how would they know, or is that just part of being an expert in this space?
It's all part of being expert, but basically, as you saw, there was this meshing thing.
Right.
So it depends on how tight mesh you make. So how much accuracy do you want? In this particular case, you have 150,000 elements, and then there is also part of the physics setup that also affects the number of unknowns you'll get.
Gotcha.
And in this particular case, there was 420,000 unknowns.
Right.
But yeah, so we don't have a solution to automatically determine this. It's a very complex problem, and because you have to take the geometry in and then the this physics definition and somehow figure out from that how big is this going to be if you want this or that accuracy. But we are planning and working on this machine learning based solution where we identify certain features of the geometry and the problem definition, and then collect data as we go, and then try to teach the AI model to predict number of unknowns, and then we can use that prediction to actually choose the amount of nodes and type of instances for the user.
Great. Cool. So yeah, let's now see the quantum demo. Impressive. We learned a thing or two today, for sure.
That's great. Great to hear.
All right. Yeah, I can present the quantum demo in just a while. Just before moving there, just a little background kind of on the quantum research and sort of the roadmap we have in there. So we, of course, kind of the first step that well, basically every quantum company takes is sort of validating if the problem they're solving actually can be solved with quantum, and that's typically done with quantum simulators. So classical computers simulating to be quantum computers, and we've done that. But also then in the summer of 2022, we had a breakthrough moment. So we were able to run a physics problem using real quantum gate-based quantum computers with accurate results. And to our knowledge, we were the first team in the world to achieve that. And I believe we might still be the only ones. At least haven't heard about. People have been running these simulations with simulators, but with real hardware, and that was due a lot to the kind of the optimization that we were able to do for the algorithms. Because right now, well, probably many of the audience and you know we are kind of in this NISQ era quantum computing, which comes from noisy intermediate scale quantum computing, meaning noisy, that they produce a lot of noise, that qubits are very short-lived, not very stable, and they produce a lot of errors in the computation. And intermediate scale, meaning that we don't have tons of qubits. I think IBM's biggest machines are at the moment about 500 qubits. But of course, when dealing with the noise, you have to dedicate a lot of those qubits to noise reduction. And kind of many of the quantum experts sort of say that quantum computers will truly be useful only in the fault tolerant phase, where actually we have come up with ways to deal with the noise. But we disagree a little bit on that based on the results we had. So I think with that I could show some of the stuff we've been doing. Just a moment, I'll have to actually. Here we go. So some of the stuff we've been doing. This is our live quantum demo. You can actually register to it and play around with it. And there's a couple of different kind of algorithms here presented. I'll actually just show today the quantum lattice Boltzmann, which is sort of our flagship method for solving CFD problems. And lattice Boltzmann might be familiar to some of you who know computational fluid dynamics. It's relatively new. It's been around for about 20 years. And it's starting to pick up traction. And what we discovered that it's actually very suitable for quantum. In a way, because it mitigates a lot of the problems that come with quantum, like, for example, the small problem that there's no quantum memory, quantum RAM available. And also it's practically impossible to input the data, input an arbitrary matrix into a quantum computer. And it's also very difficult to read out the results. But these can be neglected with lattice Boltzmann because it's sort of an evolutionary method where you can start with zero velocity field and let the system evolve in the quantum circuit. And we can actually also read out the results quite accurately. And then with a simple summation, we can get kind of the accurate results that we need. But this lattice Boltzmann here, it has a lot of math if you're into that and kind of the background on the method. So I invite the audience to go and check that out. If you're interested in that, I won't go too deep into that, and honestly, I probably even couldn't. So I'm not a math expert, but for some of the simulations that we've done, we have an example of so this was the first simulation that we ran successfully with the quantum computer. It's a advection diffusion effect simulation. So what it basically simulates is, imagine if you drop some ink or some dense liquid into, for example, water. So how it diffuses in the water. And the first one was 1D. So basically the water was abstracted into a one-dimensional, a vector basically. And this kind of shows a 1D graph of how it diffuses, and it also compares it to analytical results from classical computing and how the quantum computer actually did. Of course, when you're playing around with this demo, it's not running a real quantum computer in the background. This is using quantum simulators. It wouldn't be really practical because the runtime on those is pretty expensive. And there's also some data about the unoptimized quantum circuit. The optimized one is a little bit more hush-hush. We're not showing that around. And then we also have the same task in 2D, and we were actually also able to run this using real quantum computers. So there you could imagine that the liquid is a lake, and then you drop your ink here, and it shows how it sort of diffuses based on time. So relatively simple tasks, which can be run in milliseconds with classical computers. But the thing with the algorithms is that for the 1D problem, we needed 7 qubits. For the 2D problem, we needed 12 qubits. And the beauty of the algorithm is that with every qubit you add, we can double the size of the problem. So the problem size grows exponentially. But then again, the depth of the circuit, which is a big limiting factor because these circuits have a limited lifetime, so it can't be too high, that grows logarithmically. And that gives us the confidence that we can actually demonstrate quantum advantage in the next couple of years. Because to compute problems that are pushing the limits of what can be done with present-day supercomputers, with the Lattice-Boltzmann method, we only need about 60 to 80 qubits and about 800 CNOT gates. And that's not an unrealistic number. It's kind of the computers are almost starting to be there with sufficient noise reduction. But yeah, I'm not going too deep into the algorithms as said here, but feel free to explore this. And I think the link already flashed in the video at some point. But
yeah, I'll bring that up again.
Okay.
Yeah, you can just register in there and with your email address, and you'll get the credentials. And don't worry, we won't spam you.
Great.
But yeah, that's sort of the quantum stuff in a nutshell. And of course, the steps where we want to go from the quantum advantage, that's the point where we can start really solving relevant industry problems. And after that, basically start integrating the first quantum algorithms into our Allsolve product. So it will contain some of that stuff and the exponential speedups that our users can get.
Great. Nice. I'm going to check on this demo link which you just showed. Try it out myself.
Absolutely.
And there is a question in chat. So they're asking about what quantum backend you use, if it's something that you're willing to share.
We have experienced with a lot. So yes, Bracket, of course. But QPUs. So that's also the strategy has been that we want to be agnostic at this point. So we've been evaluating with a lot of different hardwares. We've been running with Rigettis, IonQs, IBM machines, Quantinuum machines, Atom computing. And of course with varying results. The best results so far we have achieved with the Quantinuum machines and the IBM machines. So particularly the Quantinuum's qubit topology is such that it kind of matches our algorithms extremely well, and that's where we got the best results out of at this time. Let's see how things develop in the future. It's a pretty interesting race between the hardware manufacturers.
Right. Okay. So what else is left, Tina? We have 25 minutes.
Well, what does the next 6 months or a year, like what does that look like for Quanscient?
6 months. Well, it's of course growth in sales, since we have that pretty good traction in terms of the SaaS product. So definitely going well on our way towards the first million in annual recurring revenue for the next 6 months. Well, there's obviously also kind of starting seriously on the fundraising part for our Series A round, and likely, I mean, with quantum pushing forward with the algorithms, but also kind of generating IP. So patenting is something that's kind of well, it's let's say quantum is such a green field, so there is of course an opportunity to get quite fundamental technology patents with the subjects you're researching. So for a startup, that's a big part of our kind of value to have this advanced quantum IP.
Good.
Yeah. And to add to that, on the cloud side, well, the biggest thing is to ensure that we are scalable in the cloud and we scale across multiple regions in AWS. And one rather big thing that is brewing is we are working on an SDK / API so that people could use that to access our cloud solver platform and integrate this into their own software or applications.
Okay. That would be a nice move. Like if someone has their own simulation kind of thing, just call the APIs, get the result back, then continue with their other process on the downstream.
Yeah, exactly. There are many CAD softwares that, for example, would, or they are actually using some kind of integrations to local simulators already. But this would kind of be a next level for some people. For example, we have been discussing with a certain company that does this architectural software for architects, and they are hoping to integrate with us in doing like a heat simulation of buildings, and they could just do it for like some huge apartment building or office building or whatever in one go. They would integrate it in their architect design application, so that if you make a design change in the application, you can just click a button to see how does it affect the insulation or whatnot.
And that's really the vision where we see that simulations are going towards this kind of automation in different kind of design tools.
Yeah.
Great.
By the way, there was a comment from No Namesake. I have to screenshot this so I can show it to the rest of the team. Your CEO is not so stupid.
We'll put this. There you go. Go ahead and screenshot that.
Thank you. Very kind words.
Cool.
Very nice. While we have a little lull, I'm going to go ahead and share this. We do have a survey. We love surveys. We love getting more information on what we can do better and what kinds of partners you think we should be having on our Howdy Partner Show. So definitely fill out this survey when you have a chance. It'll only take a few seconds. And we would love to know more about how you think we're doing. I'll go ahead and share that in the comments in just a second.
Sure.
So do you guys have any specific, like maybe case studies that you would be able to talk about where you've worked with a really cool customer and they've given you permission to talk about them?
Yeah, there's so of course we were quite early, so we're still kind of working on new case studies, but the one we just published recently was from a company called Skytran in California, and they're building this maglev type of public transit electric motor, and the kind of the results were pretty great in that one. So before they were using another product for the simulations, and it typically took them around 3 weeks to kind of run all the simulations, because what they wanted to get is kind of the torque vectors on how much torque the motor produces, and the geometry was quite complicated that they had to simulate in there. So there was actually, they only discovered one product before also that could actually run these simulations. And well, yeah, it took them 3 weeks. And when they compared that data against measurement data from prototypes, they were within 10% accuracy in simulations. So kind of okay results getting, but then when they switched over to Quanscient Allsolve, that 3 weeks turned into 8 hours, and the accuracy went up from within 10% to within 3% of experimental data. And that really allowed them to kind of ramp up the design cycles, and also of course rely on the simulation data, do real design decisions based on the simulations.
Nice. Very cool. Yeah, I imagine that accuracy probably turns into a much bigger deal than 7% necessarily sounds, because I could imagine if the accuracy is not there in the testing, that the products that they're coming out with could end up being seriously flawed.
Yeah, absolutely. It's I mean, a 10% tolerance is still quite high. There's a lot of room for kind of potential problems there. Within 3%, you're starting to be quite close already. So of course, still you kind of, it's still, even with our tool, it can't be avoided that you need to build a prototype at some point, and then compare what you got. But when you learn to trust the simulations, it has a huge impact on the productivity.
Yeah.
Nice.
Oh, another comment. It would be awesome to see your data designs. How did you go from 10% to 3%?
Well, most of yeah, it's, I mean, the simulations models and all were the same, but a lot to do with the higher accuracy is that we can sort of brute force these things, so we can just use a way more accurate mesh, and engineers don't have to simplify their models so much, so they're or at all, basically, because we can just throw a lot of computing power at the problem, and just that enables the higher accuracy.
Yeah, and I think one part of it was also that we were able to use this kind of, because their machine was rotating and translating at the same time, and we were able to actually do them at the same time in the same simulation and not like separately. And that's not available in almost any software.
Nice. Okay, so you have 16 minutes left. So what would be the one key takeaway message or your closing statement to our audience here?
Well, 16-minute closing statement. No.
That's a long statement.
Well, but I would definitely say we already established. Go check out the Quantum demo. It's there's a lot of background on technology there. There's also a lot of stuff about both Quantum and the classical simulations on our website, in our blog. So of course I would invite all of you to go and read some of those. Follow Quanscient on LinkedIn if you're interested, and then buy the product. So there's the comment. So absolutely, but yeah, you can get in touch with us via our website. So just book a meeting with us. We'll be happy to show you a demo and kind of discuss about the problems, and we'll be very straight with you if we see that the problem that you're doing is a good match for our product, and if we can accelerate that. So we're not kind of trying to go places where we cannot provide you the advantage. So I mean, we're Finns, we're kind of flawed that way. Too honest.
Any upcoming trade show or industry symposium you will be there, or your team will be there, potential customer can meet you?
there was just a couple of big ones, but there will be a few in Europe, and so there will be the Microtas in Poland, which is microfluidics conference, Multiphysics conference in Munich in November, about multiphysics simulations. But then probably one of the big ones, I think we will be going to the APS meeting, the American Physics Society meeting in March. Don't remember where it is this year, but well, I'll have to figure it out before we book flights. But there's still time.
That would definitely be a good idea. And then you also had a YouTube link here to share. You want to tell us a little bit about the channel that you sent us?
Yeah, there's also plenty of tutorial videos and examples on because with the demo today, it wasn't really practical to show a super large scale simulation, because even if it runs for 15 minutes, that's a long 15 minutes to wait for the results when we're live. But there's absolutely lots of impressive examples on that channel on what the software is capable of. And it also shows you a lot about how you build the models. So that's a nice channel to follow.
Any other questions or comments from anybody else in the audience? Or from anybody on the show? I'm just imagining all of the different use cases for all of this. Like, I can see, like, through, like, I know you had talked about transducers. Like, back years ago, I had a background in healthcare, and so I can see a lot of, like, healthcare and, like, medical devices type use.
Yes, absolutely. Like, ultrasound devices are very kind of and we were actually just in Montreal in early September in this ultrasonic symposium, and a lot of the kind of potential customers manufacturing ultrasound devices were there. It was a very good place for us to be.
Yeah, I could see that.
Sure.
Oh, no namesake says that they are students and that it was great to get a little more learning than what the books share.
Yeah.
Yeah.
Thanks for all the great comments. No namesake. So
yeah, that was great.
Yeah, that's awesome. I'm definitely hungry for learning more. I'm going to be watching this YouTube channel and checking it out.
Yeah,
I'm excited to see.
We'll try to produce a steady stream of content there. So
yeah.
And then, are there any other resources that you recommend, whether it's for students watching or for people who just want to understand more about the technology that you guys are creating and using?
Well, if you kind of want to know the basics of, let's say, finite element method and multiphysics simulations, there's I think I'll just have to Google it quickly, but a guy called Yusuf Murad has a lot of like content on different areas of engineering simulations. So I'll just post this super quick. So, for example, this, it's in a private chat, so but I'm sure Tina will post it in the comments section. So that's kind of a nice introduction to the finite element method, which is kind of the mathematical method we use for multiphysics, and probably the most common one for particularly multiphysics. There are other methods too, but they're typically more specialized and have a more narrow application field. But that's a nice introduction, and also a good channel to follow. There's a lot of interesting engineering content on this YouTube channel.
Nice. We'll have to take a look at that as well. All right, I'm going to put down at the bottom again, Quanscient Allsolve solution. And then in a moment, we will share out the link for the live quantum demo again. Make sure everybody has the resources that they are after. It was posted previously in chat, so I'm just going to go ahead and show it on the screen. Any last minute tidbits of advice or information that you would like to share with anybody?
Well, I can repeat what you already said, that follow us on LinkedIn. Somebody asked about the hires. Eventually we'll hire and we'll be posting on our LinkedIn about that. I don't know when it will happen, but eventually it will happen.
Oh yeah, and Finland is a lovely country, right? As I said, if someone
Yes.
wants to migrate, work for Quanscient, please.
Chance of your life.
Right on.
Absolutely. And yeah, as I said, we already have also like employees outside Finland, so working remotely. So that's also a possibility.
Nice. Very good. Well, I will refer back to the survey. Please fill out the survey. And thank you to Quanscient for being our guests on the show today. Really enjoyed having you here. Thank you for all of the information. It was great.
Yes.
That's super cool. Super awesome stuff.
Yep. I second
you
that what
for-
Tina and David said, right? It's probably 2 a.m. now. It's not easy thing to do midnight.
No.
So this is at
I'm not eager
so
to get into bed at all.
I think it's been such a nice discussion that this feels pretty easy, but I bet tomorrow morning it might not be as nice. But yeah, it's been super fun. So thank you so much for having us. Well worth it.
Thank you so much.
Awesome. Thank you all. And everybody, go ahead and make sure you tune in next week for our next partner. David, you know who we have up next week?
It looks like Alteryx.
Alteryx. That'll be cool.
Yeah.
Yay.
Cool. Okay.
Awesome. All right. Well, thank you, everybody. Have a good day, evening, or night.
Good night. Good late night.
Likewise. Thank you so much.
Bye-bye,
We'll
everyone.
talk again. Thank you.
Bye-bye.
Thanks, Tina. David.
Bye-bye.